Good morning, everyone. So now today we will discuss on one special topic of the 2 degree of freedom system, that is related to the vibration control, because often the 2 degree of freedom system can be used for the vibration control if we are thinking for the base isolated structure, or if we are thinking for tuned mass damper. Both the thing can be predominantly modeled as a single degree freedom 2 degree of freedom system. So here let's see how we can able to find out the parameters which are suitable or which are optimized parameter for a tuned mass damper or a base isolated structure. So let's first try to formulate that thing. So if you see, a tuned mass damper is like, suppose we have some structure, maybe some building. So at certain level we are using another mass with some sort of spring, so that is actually doing the vibration control. So if you see, like, first tuned mass damper is properly installed in the type I 101 building, so that is like at the around in the 60 to 70 floor range. I think specifically that is 65 stories. They have a huge mass suspended, so that act like a pendulum type thing, and once the seismic excitation happening, that mass is going to the other side, means in the out of phase, and to do some sort of vibration control. But the biggest challenge associated with it is to design that how much mass we need to put there, and what should be its stiffness, what should be its damping value for that. Because one thing we have to understood always, that we cannot put a very heavy mass on the top as the tuned mass damper, because once we are putting a very heavy mass on the top, it also increases its static load, and therefore you have to design the structure for statically very high amount of forces. So that's not a very economical choice. So identifying an optimum value for the tuned mass damper is always a very essential thing. So here today we will try to see that how we can able to optimize the parameters of a tuned mass damper and identify the and solve that type of things system. So we can understood that this type of system can be thought as like a, so that is my structure. So I can say that is a K structure, C structure, mass structure, and then I am attaching another mass which is the TMD. So MT, KT, and CT. So that is the, so first one is my main structure. So that is my main structure, and this one is my mass of TMD, and that is the stiffness of TMD, and so that is the stiffness of TMD, and that is the damping of the TMD. Okay, and other things are like a mass of the structure, and then damping of the structure, and stiffness of the structure. Okay, so these are the things. So once we are looking at this structure, so here, so now the forces are acting on the structure. So I can say that is the force acting on the main mass. So this type of problem can be also thought in the other way as well. Like, for example, suppose you are having a machine on a particular floor and you want your floor not to vibrate that much. So you put that, okay, the floor is oscillating, or means the machine is oscillating, so giving some sort of force vibration on the floor, and you try to control that vibration. So this is one of the typical case of it. So suppose if we are writing the equation of motion, how can we able to write the equation of motion? So ms mt, maybe I can just say that is us, and this is ut. Us double dot ut double dot plus C S plus CT minus CT minus CT CT US dot UT dot plus KS plus KT minus KT minus KT KT US UT F 0. that we can get. So from here, if we try to express that full thing in the Laplace domain, so we are just assuming that SU double dot equal to US into e to the power of ST, or maybe lambda t, as we are using lambda all the time. Okay, so you just use lambda t, and u of t double, sorry, not double dot, u of s equal to this, so that is a small a, and u of t equal to u of capital U of t into e to the power lambda t. That we are like using that two terms. So what will happen? So this one we will get ms lambda square plus lambda into so that way you can write, and then okay. So the first equation can be written as lambda square mt plus lambda ct plus kt into ut, that will be equal to lambda ct plus kt into ut. So u of t should be equal to lambda ct plus kt divided by lambda square mt plus lambda ct plus kt. Okay, that we can get. Now if we are substituting that one in the first equation, then what can we get? M square lambda square plus lambda cs plus ct plus ks plus kt plus it should be minus sign, minus lambda ct plus kt whole square divided by lambda square mt plus lambda ct plus kt into us, that should be equal to force. Okay, any problem up to that? So here basically what we do, we try to express that what should be the frequency response function of that displacement. Suppose if we are giving a excitation force having a frequency, so here obviously here f is actually also f into e to the power lambda t. So I can just substitute here f, so that will be capital F. So that is the amplitude. So we can able to calculate what should be the amplitude of the vibration of the of that S mass of the structure, as you can see. Okay, so we are not bothered that much with the other other structure, like for that TMD, that what is happening, but we are primarily focusing on what is happening with my main structure. So we got that. So suppose if I say that US equal to, then I can write it this times F, and my objective is what? To reduce the H lambda. Okay, if I can able to reduce the H lambda, then I can ensure that the response of the structure for a constant amplitude of the force will be minimized. So that's my objective. So now let's see. So yeah, we can able to calculate that way. Perfect. So now let's see how the response would look like. Once we are trying to optimizing it, so first let's try to see how it should look like. So here we have a small MATLAB code we did, So just assume some sort of mass ratio, frequency ratio, damping ratio, and all those, and we are try to plotting it, and you can see that we will have this type of response. So that is the dynamic amplification factor of the structure. So here you can see that if we are increasing the damping, then how the H lambda term is getting varied. Okay, so you can see that the response of that H lambda is changing like this way. So here that lambda is nothing but the omega. We can see that. So how the if the omega is varying and once it match with the natural frequency of the main structure, then you can see that total response get dropped significantly. And we can also able to have a we can also able to find a very important point here. That is, if you see that full graph is going from the 2 point, and these 2 points are act like invariant, like they are not at all changed with the damping, so they are more or less independent with the damping. So we have seen that all the curves are going through that p and q point. That 2 point are not changing, and this is like a different level of the damping. That is the damping. So the damping is varying, but your graph is like pinned with that 2 point. Now whatever you are changing, that 2 points are invariant, so all the graph need to pass through that 2 point. Now the strategy tells, and what can we get also, and we have this type of equation. So from here what can we say, that we can say that your H lambda is nothing but root over of a square plus b square into your CD value divided by c square plus d square into your CD value. That xi value is coming here. Now the important point is that once this xi value is coming here, and that the CD dependency, CD means the coefficient of the damping of the absorber, because we cannot change the structure. Like if you see that how many parameters are there, we have ms, mt, we have ks, kt, we have cs, ct. So now if you see, this full side is your constant, because that is the structure what you are going to isolate or you are going to control. So what can we change? Only we can play with this thing. So here once we are playing with that, so here this CT, which is nothing but the damping, that damping we can see that this H lambda we can write in form of the damping like this way. And we also notice that this full thing is going through this 2 point P and Q. Now that strategy tells that if we can try to make, so strategy is to make P and Q point at same response. Means whatever the response you are getting in the P point, that should be same as the Q point. How can you do? And we see that that is invariant with the damping. So the location of the P and Q point depends on what? So location of P and Q depends on other parameters. Other two parameters, other two parameters, that is mg mt and kt. It cannot be dependent on any other things because that will be just only dependent on these two parameters, because all the parameters are consumed. And now so this way it is coming perfect. And now we have to make that these 2 points same. So, and that is also valid for all the damping, same response. Okay, so if we calculate that h of lambda at cd equal to 0, what can we get? We will get a by c with the mod sign. And if we say h lambda at cd equal to infinite, what can we get? We will get mod b by d. Make sense? So that is my two h lambda values. And we can say that in these 2 points that h of lambda will be in the opposite side because they must be in the out of phase. So what can we say? A by c should be equal to minus b by d. And we can able to calculate that what are the coefficients of A, what are the coefficient of B, what are the coefficient of C, and what are the coefficient of D in terms of all those parameters. Okay, so once we can able to write that, and once we equate these two things, then from here what will happen? We will have one equation and how many unknown? Two unknown, mt and kt. But here I would like to mention one thing. That is not actually two unknown, that is only one unknown. Because mt and kt, they are not that way different. Because if you see, once we have written the equation and if we divide it by mt, then mt can be consumed and kt changed to frequency. So you can use that term as well. Okay, so by this way we can able to develop that. Thank you very much.